Okay, so hello and welcome back. So in this video we will learn a little bit about AC. Okay, now the first thing to know about AC is that basically we have already talked about DC voltages or DC signals, but about AC. Basically DC is essentially something like this, meaning that if you have the voltage across the vertical axis and if you have time across the horizontal axis, essentially voltage is not changing with respect to time, it's constant. That is AC. But then basically this is DC, but then AC comes usually in three forms. You have basically a sine wave, you have a triangular wave, and you have a something like called basically a square wave, right? So basically now the symbol that is used in order to represent an AC generator is essentially in circuits. We use this symbol over here. This is used in the schematic. This is an AC generator, and it would be I'll show you all of these basically once we get through the theory. So for now you can imagine that this is an AC generator. So what it does is that it generates AC essentially, right? Like a power supply. But essentially instead of DC, it gives you AC, right? Now, so this would essentially be a function generator. This would essentially be a function generator. Okay. Now. And of course you know that basically AC stands for alternating current. It stands for alternating current. And basically an AC wave is usually basically represented this way. So to deal with AC waves, you need to know a little bit of trigonometry, but essentially I will try to tell you to tell you about the essentials of trigonometry as we go along. That's not a problem. It's pretty simple, and but essentially this horizontal axis is time, and this vertical axis is essentially voltage, right? And a sine wave essentially goes to basically, it usually goes to some peak, and there is also a negative peak for a sine wave, and there is basically these points over here where the sine wave actually goes through its cycle. It's usually basically, for example, this is pi by 2, this is pi, this is, for example, 3 pi by 2, and this is 2 pi, right? And an AC basically, a sine wave is essentially what it does. If this is 1 and if this is -1, a sine function, meaning that if you say f of x is equal to sine x, basically what it does is that the value of the function is 0 at x is equal to 0, meaning that time is equal to 0. The value of your function is 0. At pi by 2 it becomes 1, at pi it becomes 0, at 3 pi by 2 it becomes -1, at 2 pi it becomes 0. And as a result of that you would get a function like this, right? You would get a function like this, and that is essentially a sine, the original sine function, right? Now you see essentially the same thing on an oscilloscope, and I will show you the same thing, the same on an oscilloscope as we get through this lesson. Now, of course, basically the sine wave can be changed and modified based on the situation that you have, based on the voltage that you have. What you can do is that you can represent your voltage across this vertical axis as the output of the sine function, and then the time becomes the input of your sine function, and your sine function gives you this periodic basically wave over time, right? So usually what happens is that then basically you will get a wave like this. Then when it comes to an AC wave, you would have basically, let's say that this is pi by 2, this is pi, this is 3 pi by 2, and this is 2 pi, pi by 2 pi, 3 pi by 2, and 2 pi. And let's say that this is some voltage that you have. This is the peak of your voltage, the positive peak, and this is, let's say that this is the negative peak of your voltage. And let's say that basically at 0 you're at 0, at pi by 2 you're at 1, at pi you're at 0, you're at 3 pi by 2 you're at negative 1 over here, and then you go back to 0. And then you will have this sine function essentially like this over here. You will have this sine function like this. Okay, so this is a sine function, and that's actually an AC wave. So this is voltage and this is time, right? Now basically what happens is that relative to these voltages, basically you have this level of voltage that basically means a particular thing. You have this level of voltage that means a particular thing, and and so basically you usually read your voltage from this peak to this peak, and you call that essentially V of peak to peak, or V of PP, right? And then you can also read this voltage this way, meaning that you can read it from here to here depending on what you want to do, and this becomes V of peak, V of P. And then there is a point also over here, somewhere over here essentially, and that over here, if you read your voltage at this point, this becomes V of RMS, right? Now the relationship between these voltages, so at this point essentially your voltage is 0. At this point over here your voltage is 0. At this point your voltage goes to the peak. At this point goes to the negative peak. And so basically if you read the voltage from this peak to this peak, it's peak to peak voltage. If you read your voltage from the 0 line all the way up to any of the peaks, that's the peak voltage. And if you read your voltage from the 0 line, so as you can see, this is the reference line. When you read your voltage from the 0 line all the way up to this point, and I'll tell you what this point actually is mathematically. When you read your voltage all the way up to this point, you call this the RMS voltage, right? And so what that means is that essentially now essentially the relationship between these voltages is that, of course, you can see very clearly that V of peak to peak is the same thing as 2 times V of peak, because this voltage is essentially half of this voltage, right? And also this V of RMS is basically your peak voltage times basically, or divided by square root of 2, right? So if you take your V of P and multiply it by 1 over square root of 2, meaning that if you divide this voltage over here, if you divide it by square root of 2, that gives you this RMS voltage, which is V of RMS. That's basically all that you need to know about these voltages. And so in conversion, basically, then you can always use this relationship. Use this relationship between these voltages. V of P to P is from peak to peak. It's a logical thing. Anybody can understand it. V of P is essentially from the reference line to any of the peaks, and it's always the same whether you go in this direction or whether you go in this direction. That would be basically your V of peak. And your V of RMS is essentially any of, basically, take your V of P and divide it by square root of 2, that gives you basically V of RMS, right? Now, when it comes to calculation, you need to take a couple of things into consideration, and that is so this is about, basically this is about reading the voltages that you need. Now this axis over here, this horizontal axis, is time, and there is different ways that you can use the time on the horizontal axis. We will talk about that as well. So the only thing that, I mean, the useful things that you need to know about these voltage, about the calculation here, is that the value of square root of 2, if you ever need it, is essentially the same thing as 1 point, is essentially the same thing as so the value of SQRT of 2 is the same thing as 1.414. You can take it to, for example, 4 significant figures, 1.414. And if you take the reciprocal of that, meaning that 1 over square root of 2, 1 over what is that? SQRT of 2. That is the same thing as 0.707. 0.707. So the square root of 2 is 1.414, and 1 over square root of 2 is 0.707. That you can use always in calculation, right? So square root of 2 is 1.414, and 1 over square root of 2 is 0.707. You can use this in calculation. Now, to do a couple of exercises on these voltages, let's say that, for example, you have a voltage that so for example, let's say that the V of P to, basically, peak to peak voltage of a signal is for example 10 volts, right? 10 volts, and you want to find the RMS voltage. What is V of RMS? So in order to calculate your V of RMS, what you can do is that, basically, first, in order to get the, I mean, basically, the way that I usually do it is that first I take the peak voltage from the peak to peak voltage. So essentially, you can see that over here, the peak to peak voltage is from this point all the way up to this point. This is peak to peak voltage. If I want to get the peak voltage, I have to divide this by 2. That means that essentially V of P is the same thing as V of PP divided by 2. which means that V of P is equal to basically 10 volts divided by 2, which is equal to 5 volts, right? And over here we said that basically the RMS voltage is the peak voltage divided by square root of 2, right? So which means that basically then V of RMS is the same thing as basically V of P divided by square root of 2, which means that you simply take this voltage, which is your peak voltage, and divide it by, that's essentially 5 volts divided by square root of 2, and that's the same thing as 5 divided by S 5 divided by SQRT of 2, that is equal to 3.535. I take it as 3.536. I take it as 3.536 volts, and that is of course an AC voltage. So that's essentially how you would calculate, for example, the RMS voltage from the peak to peak voltage, right? Or for example, if the RMS voltage of, suppose that you have some RMS voltage of 2 volts, V of RMS is equal to 2 volts, and you want to find the peak to peak voltage. What is V of PP, right? So to get from basically, essentially the RMS voltage is this voltage over here. If I want to get to the peak voltage, I have to multiply this RMS voltage by square root of 2, right? So I multiply this RMS voltage, V of RMS, times square root of 2 is going to give me V of P. And then if I multiply this V of P, by 2, meaning that if I calculate basically twice this peak voltage, that gives me the peak to peak voltage over here, which is what I'm looking for. So that means that V of PP is equal to 2 times V of P, which is equal to 2 times 2 square root of 2 times V of RMS, right? So that means that V of PP is equal to 2 square root of 2 V of RMS. Now you can write down these equations for yourself so that you don't have to go through this calculation over and over again. So I write it down over here as basically essentially then V of RMS times square root of 2 V of RMS times the square root of 2 is equal to V of P, and then basically 2 times the square root of 2 V of RMS is equal to V of PP. So we can use this in later calculations. And so in this case, basically I can write this as, I can write that V of PP is equal to 2 times the square root of 2 V of RMS is equal to 2 volts, which is equal to 4 square root of 2 volts, and 4 square root of 2 is the same thing as 4 times SQRT of 2 is equal to 5.567 actually, 5.6 point, I'm sorry, 5 point is the same thing as 5.657 volts. That's your peak to peak voltage. 657, right? As another example, let me write these down somewhere so that we can or I'll simply make a screenshot here. Okay, so now if, let's suppose that for example you have another wave in which essentially you have V of PP is equal to 220 volts. V of PP peak to peak is equal to 220 volts. And for example, you're looking for V of RMS. is equal to what? So over here we have a relationship between V of PP and V of RMS. So 2 square root of 2 V of RMS is equal to V of PP, right? 2 square root of 2 V of RMS is equal to V of PP. So that means that then V of PP is equal to 220 volts is equal to 2 square root of 2 V of RMS is equal to times V of RMS. And this is in volts, of course. So I can simply not write small eraser. I can simply, and that basically means that paintbrush. Okay, that basically means that V of RMS is equal to 220 divided by 2 square root of 2. 220 divided by 2 square root of 2. I have 220 divided by 2 SQRT of 2 is equal to 155.563 is equal to 155.563 volts. So the RMS voltage is 155 volts, approximately 155 volts is if no, I think I made a mistake over here. Let's see. No, I suppose I made a mistake over there. So V of RMS, of course, is supposed to be much smaller than this, because this becomes a 110, and 110 divided by square root of 2 is divided by is approximately divided by 1.5, and so that essentially becomes 0.78 volts, because you see over here your peak to peak voltage is 220 volts, right? That means that basically you have this voltage over here, and your peak to peak voltage is essentially this voltage over here, which is this voltage, which is 200 V of PP is equal to 220 volts. And so half of that would be the peak voltage, which is this voltage over here, which is half of this would be 110 volts, right? Now, so of course the RMS voltage has to be smaller than this voltage, meaning that if you divide 110 by square root of 2, that gives you the RMS voltage. Now 110 divided by square root of 2 is equal to 77.78 volts, which is essentially the RMS voltage, which is basically some voltage all the way up to only here, right? That's V of RMS, right? So you need to, of course, be careful not to make mistakes, I mean logical mistakes, and if the answer that you get doesn't make any sense, you have to rectify the problem, of course. Okay, so that's one thing. That is one thing. These are the layers. 25. Okay. Okay, then basically suppose that you have a V of RMS as for example 120 volts, and you want to find the peak to peak voltage. V of PP, right, is equal to 1. So over here again we had a relationship between the RMS voltage and peak to peak voltage, and we said that 2 square root of 2V of RMS is equal to V of PP, right? So 2 square root of 2V of RMS is equal to V of PP. So V of PP therefore would be equal to 2 square root of 2 V of RMS is equal to times 120 volts, which is equal to 240 times square root of 2, 240 times SQRT of 2, and that's about 339.4 volts, or let's call it basically 339 volts. 339 volts basically. That's their peak to peak voltage. Right. And by the way, this V of RMS 120 volts is essentially your the common house current supply voltage. This is the current. This is the now, I'm not really very much familiar with this recording setup. I apologize if I have to think too much sometimes. So this is the common house current supply voltage. This is the common house basically current supply voltage. Okay, meaning that 120 volts, RMS is the same thing as basically 340 volts peak to peak, which is what we got over here. So essentially when you connect a simple voltmeter, or when you connect a simple voltmeter to the wall outlet, and when the wall outlet reads basically, for example, 120 volts for you in your house, for example, that means that you're actually measuring the RMS voltage, meaning that essentially the voltmeter, which must be, for example, something like this, for example, some voltmeter like this, it is essentially calculating or measuring it is essentially measuring the RMS voltage for you, not the peak to peak voltage. The peak to peak voltage you could see it on an oscilloscope, for example. We will see about that in the coming videos, right? So that's basically that. Now about basically now what I'm going to do, I'm going to end this video here, and then there is a couple of things about, or let's do that over here as well, why not? Okay. So essentially, there is something called the period of an AC wave, and there is the frequency of an AC wave, and there is also something called the cycle of an AC wave. So there is the period. So there is something called the period that you need to understand. There is something called the period, and there is a cycle. And then there is also something called the frequency. So these three things you need to understand. So first of all, the period of an AC wave, if you have an AC wave over here, something like this, for example, let's say that this is pi by 2 pi, 3 pi by 2, and 2 pi, and then your voltage goes all the way up to here, and then you're at 0 here, at 1 here, at 0, at -1, at 1, at 0, and then if you have a AC signal like this, if you have an AC signal like this, so essentially what happens is that, so this is essentially one complete cycle of your AC signal, meaning that if I were to basically extend this, let me get this out of the way. It's in my, I can't see anything properly. Okay. And also this oscilloscope. Okay. So if I were to extend this to show the rest of this wave over here, so I have 1, 2, 3, and 4 again, and then again at 0 you're at, over here you're at 1. Let me draw these lines so that we can draw these properly. So over here I'm at 1, over here I'm at 0, over here I'm at -1, and over here again I'm at 0. So again I can draw this, and it would essentially look something like this. Right? So you can see that basically from at this point your AC wave is at this output, which is 0. So over here basically your output is over here you are at 0 volts. Over here let's say that you're at 1 volt, and over here you're at -1 volt, right? And this is voltage, and this is time, right? So over here at this point in time, let's call it, for example, 0 seconds. At 0 seconds you're at 0 volts, and then your AC wave is your sine wave is increasing, right? It's increasing, goes to 1, goes to 0, and then back at 0 you can see that your AC wave is decreasing, right? And then it goes to -1 and then comes back to 0. Over here again you can see that your AC wave is increasing, right? So if you pay attention to these 2 points, this point and this point over here, at this point your AC wave is at output 0. Over here your AC wave is at output 0. At this point it is increasing, and again at this point it is increasing. So from this point in time all the way up to this point in time, this time interval is called the period of your AC wave. It could be any interval in time, but whatever it happens to be, this becomes the period of your AC wave. For example, it could be, for example, I don't know, 5 nanoseconds, it could be 5 microseconds, it could be 5 seconds, it could be 5 anything. But whatever it happens to be, these 2 points, basically the time period between these 2 points becomes the period of your AC wave, right? Now, so and basically this is called then one complete cycle of your AC wave. So one complete cycle means that basically your AC wave essentially starts from basically this output, which is 0, and goes back to a point where your output is again increasing and at the same output. So between these 2 points you can see that your wave is at the same output, and at both of the 2 points basically your AC wave is essentially increasing, right? So that becomes one complete cycle of your AC wave. And of course, then relative to your cycle, then you can say that basically the time period that it takes your AC wave to go through one complete cycle is called the period of your whatever you want to call it, the period of your AC wave, right? Now, what happens is that then there is also the frequency, and the frequency is a measure of how many complete cycles you have per basically in 1 second, right? So so when you say that, for example, an AC wave has for example is the frequency of an AC wave is, for example, I don't know, 100 megahertz. That means that there is 100 megahertz is the same thing as 100 megahertz is the same thing as 100 basically into 10 100 into 10 raised to the power 6 hertz, right? Which is the same thing as 100 million, which is the same thing as 100 million hertz. And 100 million hertz is the same thing as 100 million cycles per second. Cycles per second, right? So in order essentially to calculate your frequency, all you need to do is that you take your period and divide it by and take the reciprocal of your period, right? So essentially whatever your period is, if you take the reciprocal of your period, you will come up with basically your frequency, which is how many cycles you have per 1 second, right? And of course you can calculate that as well directly. I mean, you don't have to really have to memorize this. I'll show you a way using simple proportions to derive this on your own as well. Okay, so now in order to basically I said that I would show you how you can calculate your frequency from your period. And essentially your period is the amount of time it takes for one complete cycle to occur, right? So this essentially means that let's suppose that basically one complete cycle occurs in, for example, in t seconds, for example, right? So one complete cycle essentially occurs in t seconds. So now if you want to know, so essentially that means that I can write this as a proportion as one complete cycle in, or one cycle in basically in t seconds. And so if you want to calculate basically how many cycles occur in 1 second, so then if you cross multiply here, you'll get x is equal to essentially one cycle times 1 second, and divide that by t seconds, and second cancels out, and so x would be equal to basically one divided by t is equal to 1 divided by t cycles, right? So that means that the number of cycles that occur in 1 second is equal to 1 divided by t cycles. So that basically means that the frequency of your wave, that means that the frequency of your wave, which is essentially the amount of cycles per second, would be 1 divided by t, 1 divided by t, essentially cycles per second, right? So that means that, and over here you can see that basically the period of, I took one complete cycle as t seconds. So essentially whatever the amount of whatever your period is, if you divide it by, if you take the reciprocal of that, and if you give it the unit of cycles per second, that would be your frequency, and that would be the same thing as 1 basically divided by t, 1 divided by t, essentially cycles per second, you can call it hertz basically, right? So long story short, what that means is that whatever your t, basically your period is, whatever your period is, 1 divided by t would be your frequency. And basically the frequency, and basically your period is in seconds, and your frequency is in cycles per second, which is the same thing as hertz, right? Okay, so that is basically that. Now, to go through some terminology here and to do a short recap, essentially what we know is that one complete basically sine wave, or basically one complete cycle of a sine wave is called I'm sorry, I made a mistake here. Let's say that basically one complete sine wave, which is essentially by that I mean basically the sine wave starting from here, going through one complete cycle. If we call that basically one complete sine wave, that is basically called a cycle, right? And the time it takes to complete one sine wave, basically the time required for one complete cycle, is basically called the period, right? And then the frequency of a sine wave, the frequency of course would be the frequency of a sine wave would be the reciprocal of the period, right? Of the period. And then the unit for frequency, and then the unit for frequency, would be basically cycles per second, or you can call it also hertz, which is also denoted by Hz, right? And now suppose that as an example, let's suppose that, for example, the period of a sine wave is 0.5 milliseconds. The period t is equal to 0.5 milliseconds. Now you want to calculate the frequency, right? So if t is equal to 0.5 milliseconds, your frequency would be equal to 1 over t, which is equal to 1 over 0.5, basically 0.5 cycles per, and this is in milliseconds, right? And that is basically your frequency. And so 1 over 0.5 is essentially 2, and 2 basically this is 10 raised to the power. You can write this essentially as 1 over basically 1 over 1/2 is the same thing as 2, and then you can write this as 1 over basically 1 over 2 into 10 raised to the power negative 3 seconds. And of course this would be a cycle over here, right? So the frequency would be so many cycles per so many seconds, right? So this would be the same thing as essentially 1 over 1/2 is equal to 2 into 10 raised to the power, this goes to the numerator, becomes 10 raised to the power 3 cycles per second, and 2 basically that would be basically 2000 cycle per second would be hertz, and that's the same thing as 2 kilohertz, right? That is the same thing as 2 kilohertz. So and let's suppose that, for example, if for example you have a sine wave, the frequency of a sine wave, if you want to calculate the frequency of a sine wave with basically a period of 40 microseconds, if t is equal to 40 microseconds, right? If t is equal to that, then you can calculate this using this. Okay, so now if your period is 40 microseconds, so this is something that you need to, of course, to understand properly, because you're going to see this on an oscilloscope over and over again. And the way that you can, if your period is basically 40 microseconds, that means that you would have a wave, or a sine wave, that basically looks something like this, right? It looks exactly, or something, essentially something like this. It goes from 0 to 1, and these are supposed to be drawn better than this, but essentially it would look something like this. Essentially it would look something like this, right? Now this is one complete cycle of your sine wave, meaning that at this point your output is 0, at this point your output is 0, at this point the function is increasing, again at this point the function is increasing. So that means that this, basically from this point all the way up to this point, this is one complete cycle. This is one complete cycle. Now the time required for this one complete cycle is called your period, right? So the time required for this, the time t is equal to, t would be your period, which is denoted by t, right? So if you had a sine wave whose period was 40 microseconds, that means that basically your wave essentially is something like this, and then you look at your oscilloscope screen, you look at we will look at basically a couple of waves on the oscilloscope. You would look at your oscilloscope screen, and then you would see that basically you had basically a sine wave like this on your oscilloscope screen, and this goes from this point to this point, one complete cycle, and then you read on your oscilloscope that the sine wave is essentially from this point to this point. It takes 40 microseconds for the wave to go through one complete cycle, right? And so now you want to calculate the frequency of this wave, meaning that you want to know basically you know that in 40 microseconds, which is this time interval, in 40 microseconds your wave goes through one complete cycle. Now, how many seconds is it going to go through one complete cycle, right? In how many seconds is it going to go, or essentially in 1 second, how many of these cycles are you going to have, right? So the way that you can calculate it is that you can set up the same equation. Essentially, you know that F is the same thing as basically 1 over T cycles per second. Cycles per second. Of course, this is provided that I'll show you what I mean by that. So your F, your frequency, would be equal to basically one cycle divided by or essentially 1 over T cycles per second. That is essentially the same thing, so I don't have to write that anymore, really. So essentially your frequency would be equal to 1 over basically 40 microseconds, and that would be one cycle per 40 microseconds, right? And so what that means is that it's the same thing as 1 over 40. 1 over 40, basically 1 over 4 is, that's the same thing as basically 1 over 4 into 10. And over here you have 10 raised, micro is the same thing as 10 raised to the power negative 6, of course, right? Micro is the same thing as 10 raised to the power negative 6 seconds, and over here you have one cycle. So that basically becomes basically 1 over 4 times 10 raised to the power negative 5 and cycles per second, which is the same thing as basically 1 over 4 is 0.25 into 10 raised to the power 5. Cycle per second is hertz, right? And that's the same thing as basically 2.5. That's the same thing as well. You can call it, for example, 25,000 hertz, which is the same thing as 25 kilohertz, right? 25 kilohertz. Right, so that is basically that. Now the next thing that we have, let's do another example over here. So let's say that the frequency of a sine wave is 60 hertz, for example, and you want to calculate the period. So if the frequency is 60 hertz and you want to calculate the period, right? So when you say that the frequency is 60 hertz, that means that the frequency is 60 cycles per 1 second. Per 1 second, right? So and therefore your period, your t, would be equal to basically 1 over your frequency in seconds, 1 over f in seconds. And the reason why that happens is that over here we are saying that we have basically 60 cycles in 1 second. 60 cycles in 1 second. Now when you want to calculate the period, you want to know basically for one cycle, what is the time that it takes for one cycle to complete, essentially. And that is equal to the time that it takes for one cycle, and that is equal to x, for example, right? So your x would be equal to essentially one cycle would be 1 cycle times 1 second times 1 second divided by 60 cycles, right? So cycle and cycle will cancel out. You have 1 divided by 60, 1 divided by 60 seconds. So that means that if you have 60 cycles in 1 second, then essentially the time required for one cycle is 1/60th of a second, right? And that is called your period. So your period is essentially 1/60th of a second. And 1/60th of a second is essentially 0.01666 and so on and so forth. For example, you can take 3 significant figures, you get 0.0167 seconds, right? Or which you can call basically 1.67, which you can call essentially 1.67 into 10 raised to the power, for example, -2 seconds. Or you can call it basically 16.7 into 10 raised to the power -3 seconds, which is the same thing as 16.7 milliseconds. In electronics, of course, you know that it's not very, the right way of writing this number would be 1.67 into 10 raised to the power -2 seconds, which is the scientific notation, but usually we don't deal with these types of numbers in electronics. In electronics, you want to write your number in such a way that it becomes something like a millisecond, or for example, a millisecond, or for example, a microsecond, or a nanosecond, or a picosecond, or something like that. So usually you want to write your numbers so that they become, so that you get a factor of a multiplier of 10 that has a power of -3 or -6 or -9 and so on and so forth, right? And then you can write it as, for example, 16.7 milliseconds or so. Or for example, let's say that you want to calculate the period of a sine wave with frequencies of, for example, if the frequency is for example 12.5 kilohertz, right? 12.5 kilohertz. If that is your frequency, then your period would simply be equal to 1 over basically your period would be 1 over f in seconds, of course. So this is the same thing as basically 12.5 and then 2 zeros in hertz, right? So then your period would be the same thing as, for example, 1 over 12,500 in seconds. 1 over 12,500 is the same thing as 18 to 10 raised to the power -5 is 8 into 10 raised to the power negative 5 seconds. So you can write that as you can write this as, for example, 0.8 into 10. I can write it as, for example, 0.80 into 10 raised to the power negative 1 into 10 raised to the power negative 5 seconds, and that would be 80 into 10 raised to the power negative 6 seconds, which is equal to 80 microseconds, right? Or, for example, if you have a wave that has a frequency of, for example, 1 megahertz. If the frequency is 1 megahertz, then essentially, so that's the same thing as 10 raised to the power 6 hertz, right? So then your period would be 1 divided by this, so that would be 1 divided by 10 raised to the power 6 seconds, which is the same thing as basically 10 raised to the power negative 6 seconds, which is basically 1 microsecond, right? So that is 1 microsecond. Okay, so this was basically all that you need to know about all the calculations of time and amplitude related to these sine waves. So now what I'm going to do is that in the next video I'm going to show you a couple of sine waves on the oscilloscope, and we will probably do some calculations as well, and we will measure some voltages using some basically digital multimeters and oscilloscopes and things like that. So I'll see you in the next video, and thank you.